We have talked about the dependent motion analysis, which involves pulleys and cables. We've also looked at a simple example which illustrates the concept. Now it's time to look at a more complicated problem, which is a typical problem that one might face in an exam. So here we have a cable B, which is pulled downwards at 4 feet per second, and the speed is decreasing at a rate of 2 feet per second squared. We're asked to determine the velocity and acceleration of block A at this instant. So I would like us to look first at the image and analyze it carefully. So the very first thing to note is the difference in ropes. So here we're actually faced with a cable and pulley system which involves two different cables. There's one cable that's running from the upper wall towards A, then D, then C, that's the first rope. Then we have another rope or cable that's going from the bottom or the ground to C, then from C to B. And that's very important to note. So I would give you a couple of minutes to try to solve it on your own, and whenever you're ready to look at the solution, just continue the video. The first step, as we have already seen before, is to write down what we know. We know that we're working with a cable and pulley setup, so it means that we're faced with dependent motion. The motion of one of the particles or points, like point B, affects the motion of point A. We're also given the velocity of B, which is 4 feet per second, downwards, and the acceleration of B, which is minus 2 feet per second squared. So if VB is going downwards, the acceleration is negative, so it is impeding the motion downwards. And so the direction of A is upward. The second step, as we have seen in the lecture, is to select the datum lines and to set the positive direction away from the datum. So you are free to select whatever datum you want for any particle you're working with. Here we're dealing with two main particles, B and A. And so if we want to select datums, let us select the first datum for A to be the upper pulley, the ones that's directly attached to the wall. Let's call that D. That's our datum. The second datum for point B would be the ground, the bottom ground. And so if we want to pinpoint the different locations, we can simply make use of these datum lines. And remember, the positive direction is always outwards. So if your datum, the very first datum that's above, next to D, the positive direction would be downward, while the second datum, which is on the ground, has the positive direction, which is upwards. Next, we need to identify the different ropes. As I have mentioned before, we're actually faced with the two cable setup. The first cable runs from the upper wall to A, then to D, then to C, while the second rope goes from the ground to C, then from C to B. So we have two ropes, and that's important to keep in mind, because the number of ropes you have gives the number of equations you can work with. The next step is to write down the equations, summing up the portions of each of the cables. So if we want to sum up the portions of the first cable by identifying the position of particle A, particle B, particle D, or particle C, one can write that 2SA, which is the length between the upper wall and the pulley, which identifies particle A, plus H, which is the total distance between the upper pulley and the ground. Remember, that's a constant, since the upper pulley cannot move and the ground cannot move as well. So H is always a constant. So we can make use of that to identify the third chunk of the rope that's between D and C. So the distance DC can be written as H minus SC. And so all that's equal to L1. Now if we want to sum up the different chunks that constitute the second pulley, and so that's the distance from the ground to C plus the distance CB, one can write SC plus SC minus SB is equal to L2. Now, if you can't understand why we've derived these equations this way, you can simply refer to the schematic which is shown on the right. Now that we have the two equations at hand, we can take the derivatives to get the velocity components. So from the first equation, taking the derivative, we get 2VA is equal to VC, since H and L1 are constants. And from the second equation, we get 2VC is equal to VB, since L2 is a constant. Now combining 1 and 2 together to get a relationship between VB and VA, one has VB is equal to 4VA. And so if one wants to find the velocity of A, VA is equal to VB over 4. Now it is time to replace the velocity VB with the value of VB and the sign convention adopted based on the datum lines selected. So we know that VB in magnitude is equal to 4 feet per second. We also know that the positive direction for the datum related to B is positive upwards. So since the velocity is downwards, it needs to have a negative sign. So that's minus 4 over 4. And so VA is equal to minus 1. Now that we have VA is equal to minus 1, we need to find the direction of VA. Since VA is negative, it is opposite to the positive sign convention adopted. Now looking at the datum related to A, we know that the positive is downwards, so the negative is upward. And so VA is 1 feet per second upwards. The last step is to take the derivative of VB equals to 4VA in order to get an expression for the accelerations. So AB is equal to 4AA, so AA is equal to AB over 4. And we know that AB is equal to 2 feet per second in the upward direction. Now looking at the datum we've selected here for B, the upward direction is positive. So here we write AB is equal to 2, which is divided by 4, gives us 0.5 feet per second squared. And now if you want to find the direction of AA, since AA is positive, it follows the positive sign convention for the datum, which is downwards. And so AA is equal to 0.5 downwards. It is very important to keep in mind the sign conventions we've adopted by selecting the datum line. So whatever value you come up with for VA or AA, it is always related to the sign convention you've adopted for the datum line. Whatever datum line you've selected for A or for B should always end up with the same final answer, which means that VA is equal to 1 feet per second upwards, while AA is equal to 0.5 feet per second squared downwards.